Hi, everybody. This is Mr. Folly, and welcome to Podcast 1.2. We're going to talk about average atomic mass. Average, hey, that's a math thing. Band of stability, that's just a graph. Determine the half-life, hey, that's math too. Determine the age of radioactive substance, hey, we're going to talk about math. Get out that calculator I told you would need and love in class, and get ready to rock this bad boy, because I am ready myself. Atoms come in enormous groups that will always have the same average atomic mass. Now we're talking enormous groups. What do I mean by enormous? I mean like 10 to the 20th or so. That means I don't have one atom, I don't have 1,000 atoms, I don't have 1,000,000 atoms. I have 19 zeros on there. Woo! So huge amounts. So if you have huge numbers, the average number is going to be the same. So to find the average mass, you're going to have mass 1 plus mass 2 plus mass 3 plus mass 4. So let's pretend there's, to give you an idea, a parallel on this, pretend there are only two types of dogs in the world. There's the big dog. Big dog weighs 2,000 pounds. That's a dog. And then there's the little dog. Little yippy dogs, they weigh 2 pounds. Okay? So if this dog weighs 2,000 and this one weighs 2, you go, well, what's the average? Well, you might think add them together and divide by 2. But really, what if 90% of the dogs are big dogs that weigh 2,000 pounds, and only 10% of them, 10% of them weigh 2 pounds? Then wouldn't the average mass, because the percentage is so much closer to this, be closer to 2,000 than 2? So the average mass of a huge number of dogs would do that. Okay? So just to give you an idea of this. Multiplying by the percentage, adjust the value based on the ratio being less than 1, right? The mass can't be over 2,000 because it can't be more than that, and it also can't be over 2 pounds. It's got to be that ratio, and multiplying by the percentage. Now notice I use the decimal form of the percent, and to get the decimal form of percent, you move the decimal over 2. So let's do some examples. Uranium, not my uranium, uranium is used in nuclear reactors and is a rare element on Earth. Uranium has 3 common isotopes. Uranium-234, hey, that's the mass, is 0.01. The abundance of uranium-235, hey, that's the mass, is 0.71. And the other abundance is 238. Notice it's not just 234, 235, 236. They're kind of out there. Okay? So what we're going to do is, remember, it's mass 1, percentage 1, plus mass 2, percentage 2, plus, in this case I have 3 of them, right? Get back there. Come back, come back, come back. Mass 3, percentage 3 equals. Okay? So I'm going to put those numbers in there. So my mass of 234 times not 0.01, 0.0001. Ah, the decimal. And then 235, not 0.71, 0.0071. And then mass 3, 238, not 99.28, but 0.9928. So I moved the decimal 2 spots on each of those. Got out my handy-dandy little calculator. 234 times 0.0001 plus 235 times 0.0071 plus 238 times 0.9928, and my answer should be very close to uranium-238, and it is. It's 237.98 AMU, and the units for these masses are atomic mass units. Almost all of them are uranium-238. Well, look, that mass is really close to 238. Magnesium has 3 naturally occurring isotopes. Percentage bunch of these isotopes are as follows. Boop, 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 boop. Okay, so there's my percentage, percentage, percentage. Now notice we just had 24, 25, and 26, but they gave us real numbers for it. Okay, now this one's trickier because we're going to use the same equation, M1 percentage 1 plus M2 percentage 2 plus M3 percentage 3. But I'm going to read this problem to you. The average mass of the 3 isotopes is 24.350. That's that number. Okay, so I'm not solving for that this time. And then they give me the atomic masses of each of these, okay? So they give me atomic mass of 25. That was my second one. Whoops. And they give me the mass of 26. That's that one. And it asks me to find this guy right here. Okay? So it's just an algebra one where I have a different variable. Okay? Calculate the actual atomic mass of magnesium 24. So that's what I'm looking for is magnesium 24. I don't know. Well, I guess I'll call it 24. Why not? I know the percentage of it is not 78, but 0.78. The mass of number 2 for 25 is 24.98. 584, and that percentage was not 10.13, 0.1013, and then, oh, get back here, and then the last one, the percentage was, I'm sorry, the mass was 25, let me make sure I did that right, so I'm looking for the third one, 26, there it is, 26 is 25.98259, and that percentage was 0.117, and then that equaled 24.305. Okay, this is terrible writing on my part. Okay, let me rewrite that, 0.117. So then all I'm going to do is the math to figure out what that's going to be. Okay, so I'm going to chunk this out a little bit. 24.9854 times 0.1013 is 2.531. 25.98259 times 0.117 is 3.03996. Now just give as many numbers as I can remember. Equals 24.305. And this is at, well, I'm going to change it to be a more traditional way. Come on, get back there. Of 0.787 m. Okay, so now I'm going to collect my terms. Nope, I'm going to try to collect my terms. So 24.305. Remember to get rid of these as you do the inverse operation. These are added on the left, so I subtract them on the right. 24.305 minus 3.03996 minus 2.531 will give me 18.73404 equals 0.787 m. To solve for m, remember you do the inverse operation, right? These are multiplied, so you're going to divide. So my 18.73404 is going to be divided by 0.787, and I get 23.804. Okay. And that should be kind of, oh, that's not right. That means I messed up my math. Well, here's your first extra credit opportunity of the podcast. Can we figure out what the real math answer is? Because Mr. Folly fat-fingered a calculator and messed it up. Oh, do you have a question? Okay, grab a seat. You're fine. Sorry. But the chance for extra credit is rare and wonderful. Okay, an element has two isotopes. Isotope A is 74.6%. Isotope B is 25.4%. Which isotope has its mass closest to the average mass? Now, you see how these percentages are different? 74.6 and 25.4. It's A because it has a bigger abundance. And abundance is the percentage. That's it. I like those questions. Those make me happy. An element has three isotopes, A, B, C. Which has the closest, which isotope has its mass close to the average atomic mass? Well, this is my biggest percentage. This is that. So it's A, same reason. So hopefully now you know how to predict and guess and do all that wonderful stuff. Good. Some nuclei have an unstable proton to neutron ratio and they decay into another substance. So right here, this is the band of stability. That means you are happy. Woo-hoo-hoo. That means you're not falling apart. You're usually falling apart when you're unhappy. Okay. So if you are off this band of stability, so if I plotted this and I did over 10, no, get back here, over 10 up 30, this would be unstable. And that means you're going to do beta emission. Okay, we talked about this a little bit before. Okay, and over here, if your proton-neutron ratio is here, you're going to be unstable and you're going to do positron emission or electron capture. Okay, now what I don't like about this table is anything in this area I'm shading right here is unstable, and it's going to be alpha decay. And that bad boy happens at 83, anything with 83 protons or more. Yeah, so it's unstable, and it does alpha. Good. Neutrons are like glue. Too much glue and the bond won't work. Not enough glue and the bond won't stick. That's why they're unstable. This decay occurs in a half-life manner. So what that means is it keeps getting cut in half, and half, and half, and half. It's not a linear decay. Okay. So we can find the amount left, the amount in the beginning, and the half-life. So let's do that. The half-life of argon-42 is 28 days. If the sample contained 510 grams, how much would remain after 140 days? How much is present 56 days ago? So what I do here is I do an amount, and I do a on one side, and I do a table with time on the other. So I know the half-life is 28 days, and I know it starts with 510. And at time 0, I have 510. So every step in the procedure, I'm going to add 28 days. 28, 56, 84, 112, 140. Oh, that's where I want to stop. And every time here, what I do, so every time I go here, I add a half-life. Every time here, I divide by 2. So 510 divided by 2, 255. Divided by 2, 127.5. Divided by 2, 63.75. Divided by 2, 31.9. Divided by 2, 15.9. I'm going to write that over here. 15.9 grams. See, that's nice and organized and easy to do. And then how much was present 56 days ago? Now this one's a little tougher, okay? So same idea of amount and time. But here I'm going to start with it at the bottom because it's an ago, okay? So 510 so if the amount I have is 510 and my time is now, if I'm doing the ago, this is going to be 28 days ago, and this is going to be 56 days ago. So do you see how this time I'm going to be multiplying by 2, okay? So 510 times 2 is 1020. And here, notice how we would be adding 28. Here we're subtracting 28 going backwards. So then 1020 times 2 is 2040. And that would be grams. Yay. Okay. I'm going to skip that one just because my time's running a little late here. 20 grams radioactive isotope are present at 1 o'clock, and 5 grams remain at 2 o'clock. What is the half-life of the isotope? So here we go. We got an amount. And a timetable. So I start with 20, and at time, time 0. And then I am going to cut this guy 10, and then cut again and get 5, okay? So my time went from 0 to 1 hour. How'd you get that? 1 p.m. to 2 p.m. is 1 hour. So that means I had 2 half-lives. 2 half-lives equals 1 hour. So that means 1 half-life. Get back here. Whoa. 1 half-life equals, boy, they're really making this harder on the math, equals 1 over 2 hours, or half an hour. And we're going to stop at this one. I thought I could fit more on my podcast, but we're going to have to wait for carbon data until next time. So toodles. Look at all that reviewing. How exciting. Duh.